Good afternoon. Welcome to our 1:30 press conference, Natural or Man-Made, Triggers and Limits to Induced Earthquakes. We have three speakers, and they will speak in this order. Art McGarr of the Earthquake Science Center of the U.S. Geological Survey in Menlo Park, California. Austin Holland, research seismologist with the Oklahoma Geological Survey in Oklahoma City. And Cliff Frohlich, Associate Director and Senior Research Scientist with the Institute for Geophysics at the University of Texas at Austin.
Well, welcome everybody. Thanks very much for coming. Today I'm going to be, thanks. Today I'm going to be talking about some of the factors that influence how large earthquakes might possibly get for particular activities that involve fluid injection at depth. Let's see. Okay, so I think everybody here already knows that induced earthquakes, especially associated with oil and gas activities, have been reported more and more frequently as time goes on. Many of these involve the production of natural gas from low permeability shales. Because of these new technologies, we're in the middle in the United States of a major gas and oil boom. The new technologies involve large volumes of fluid injected into geological formations, and this leads to induced earthquakes. These earthquakes, as you all know, are sometimes large enough to be of concern to the public and get reported in the newspapers, and there's obviously a need to assess the hazard due to these earthquakes induced by fluid injection, and that's what's motivated my recent efforts that I'll talk about here. So this is a map that of the major shale plays in the United States. I'm just showing this to indicate that the future probably holds a lot more reported induced earthquakes as the gas boom expands more and more in the coming years. This cartoon shows a fracking well on the right. I've got a pointer. A fracking well, which also serves as the gas production well. But in any case, initially, water is pumped into a shale, a low permeability shale formation, such as the Marcellus in the northeastern part of the U.S. It's fracked at intervals along the horizontal portion of the borehole to cause cracks to propagate through the shale and increase the permeability to allow natural gas to be produced readily. In addition to the natural gas that's produced, however, there's a lot of wastewater also produced, and this wastewater has to be disposed of, and the common practice is to inject it into deep wells into aquifers that are well below the shale horizons. So a common scenario is for the wastewater disposal, and the wastewater disposal is what's primarily responsible for most of the earthquakes that you've read about in the last few years. In any case, the wastewater is injected into a deep aquifer. The aquifer in turn communicates the increase in pore pressure from the well bottom to a to a nearby fault, and the increase in pore pressure will cause earthquakes to occur. So the question is, how big might these earthquakes be for a particular injection wastewater disposal activity? Now, what's plotted here is the maximum magnitude going from low magnitudes 1.5 down here up to magnitude 5.5 here. And then on the horizontal axis, it's the total volume of injected liquid up to the time of the earthquake. So most of these, the points representing various case histories here are for wastewater disposal. Two of the exceptions are these enhanced geothermal systems wells, one at Basel, Switzerland, where a magnitude 3.4 earthquake following about 11,000 cubic meters of water injection had serious consequences, as many of you know already. This was back in 2006. In Australia, in the Cooper Basin, out kind of in the middle of nowhere, north of Melbourne, a larger volume of disposed injected water into a granite formation caused a magnitude 3.7 after 20,000 cubic meters of water. But this earthquake had no consequences at all because it's a fairly unpopulated area. So location is all important in terms of the seismic risk associated with these injection activities. But the main point I want to make here is that from this distribution of magnitudes as a function of total volume, injected volume, there appears to be an upper bound. And this blue line was calculated based on the assumptions that were ideal for producing earthquakes, which I don't have time to get into here, but there is a basis for this line, and everything is physically reasonable as to why there is this upper bound to magnitudes for these earthquakes. And I think that one of the main points I would like to make here is that I think we're at the point where, if you tell me that you want to inject a certain amount of wastewater, for example, 1 million cubic meters here, in a particular activity, I can tell you that the maximum magnitude is going to be 5 or less. I emphasize or less because these earthquakes are the ones that have made the newspapers. They're not typical earthquakes. They're the biggest earthquakes in their size range. Now, the somewhat more controversial finding in this study is that injection rate, or equivalently the bottom hole pressure, the pressure in which the fluid is injected, does not seem to affect the maximum magnitude. Here we see on the horizontal axis the injection rate. This is 10 to the 4th cubic meters a month, 10 to the 100,000 cubic meters a month. There's about a factor somewhat greater than 30 between the lowest and the highest injection rate. But the main point here is that there doesn't seem to be any dependence of maximum magnitude on the injection rate. Whether you inject slowly or rapidly, you'll get much the same result in terms of the maximum sized earthquake. If you inject at a high rate, of course, the earthquakes will occur more frequently, but the maximum magnitude will remain the same. So that brings me to the conclusions. The main conclusion is that the upper bound magnitude appears to be controlled by the total volume of injected liquid. The rate doesn't seem to matter, and an implication, of course, is that with time, as an injection activity continues, so will the seismic hazard as measured by the maximum magnitude. So thanks very much. Changed the
where's the So I'm going to talk about some broad-scale observations we've made in Oklahoma and to discuss some of the implications. I apologize, some of my figures were originally designed for black backgrounds, and there's a link on the back of the handout which is a little easier to see on a black background, but there's the black background links there at the end of the handout. So earthquakes have become much more significant and frequent in Oklahoma since the beginning of 2009. There are some or many that have suggested these earthquakes have to be due to oil and gas production within Oklahoma. And my conclusion at this point is likely that some of these earthquakes are caused by oil and gas production, but no changes in oil and gas activities are immediately apparent that could explain the dramatic rise in earthquake rates. So this is a map of the earthquakes in Oklahoma from 1882 to 2011. Oklahoma has a long history of having earthquakes, both in the historical record as well as the geologic record. Most of the seismicity is concentrated within the central portions of the state, near but not necessarily on large tectonic faults. And the tectonic faults are shown as the thick black lines, and the earthquakes here are scaled by magnitude, their symbols and their pluses. So you can see that there's a large number of earthquakes within the central portion. Our recent increase in earthquake activities we'll see in the next slide is occurring primarily in this region, although it's occurring throughout the state. So this is examining the earthquakes within each of these regions. And so the only places in which we don't see an increase in earthquake rates is in the western portions, in these pink and green boxes here in the western portion of Oklahoma. All the other regions show at least some minor increase in the rate of earthquakes. So we can see here the number of magnitude 3 earthquakes through time, and here in 2009 you can see these really large spikes. Those are occurring here in the center yellow patch in this kind of brownish color to the east of that. That is the Jones Swarm and the Prague aftershock and our magnitude 5.7 that occurred last November. So that's our area of greatest earthquake increase, but we do have other regions that have seen an increase in earthquakes, such as southeastern Oklahoma here. So triggered or induced earthquakes can be caused by fluid injection at depth, as are indicated. Oil and gas activities use fluid injection at depth to dispose of salt water, increase production through water flooding, and also to perform hydraulic fracturing and stimulate wells. All these activities have been shown to cause earthquakes in some cases. Cases of earthquakes caused by hydraulic fracturing may be the easiest to identify because of the very short duration over which hydraulic fracturing occurs. It occurs over days or weeks, and so that makes it easier to then look for cases where we might have earthquakes triggered by hydraulic fracturing. So there was one such case that is currently in the peer review publication process, and we saw more than 85 earthquakes. We got really good locations for those 85 earthquakes. They're located on a fault that trends roughly like this, about 2 kilometers from the well that was being hydraulically fractured. This well is a little bit different than a lot of the wells that are being completed in Oklahoma because it's a vertical well. The largest earthquake was a magnitude 2.9, with several earthquakes being felt, and about 16 earthquakes of magnitude 2 or greater. One of the interesting things is this occurred near a large concentration of historical seismicity there in the south central portion of Oklahoma. And this study would not have been possible without the additional stations that were provided by the NSF EarthScope transportable array. So it really made a huge difference to have those stations available to us. We would have known about the largest earthquakes in the sequence had we only had the regional seismic stations to use for this analysis, but the additional seismic stations really made this study possible. So this is a view of the injection at the for the hydraulic fracturing, and so here is pressure, and down here is the injection rate, and total volume is this gray dashed line, and the number of earthquakes are shown here, summed by hour. And so you can see that most of the earthquakes occurred during the second frac stage. There's a multiple temporal correlations. During the hydraulic fracturing of this well, a blizzard came through Oklahoma and shut down operations at the well, and the earthquakes decreased through time after they shut down, and then when they started back up again, the earthquakes began to occur again as well. So there's a lot of wells that have been completed within the state of Oklahoma. There's been about 5,000 wells in the last 2.5 years, and this shows where they've been completed number-wise through the different regions during the time frame. And so the greatest number of completed wells are here in the northwestern section. The smallest number of completed wells in any of these regions are the two regions which saw the largest increase in earthquakes. So this is another aspect. I mentioned that it's fairly easy to identify potential cases of induced seismicity from hydraulic fracturing because of the short durations. So I decided to look at this, let my computer look for these other cases, because I identified some visually, just identifying where a well had been completed and earthquakes had occurred within a few days' time of that completion. So I'm looking at a spatial window of about 8 kilometers, and then I'm also looking at a temporal filter where the cross here represents the well completion time, and I'm looking back 21 days before the well completion time listed in the Oklahoma Corporation Commission database. And doing this, I identified 96 different wells that could have triggered earthquakes. The average uncertainty of my earthquake locations is about 7 kilometers, which is partly why this spatial filter of 8 kilometers was picked. And the mean completion time the mean lag between earthquakes and completion time was about 11 days. So the largest earthquake identified using this technique was a magnitude 3.4, and there were 10 earthquakes greater than magnitude 3, including the 3.4. So this represents that 96 wells represents about 2% of all, a little less than 2% of all wells completed in the 2.5-year time period I looked at. And if we were to attribute all those earthquakes to being caused by those hydraulic fracturing operations, it would be roughly about 10% of the earthquakes occurring during the time period. So one of the questions I had to ask is, could these be a coincidence? We've had a very large number of earthquakes occurring in Oklahoma, and we've had a very large number of wells being completed, and could it just be a random coincidence with these two different things going on at the exact same time? So what I did was I created 1,000 synthetic earthquake catalogs with randomly located earthquakes throughout Oklahoma over the same time period and over the same rates that the earthquakes were occurring, and I identified between 20 and 82 wells that may have triggered earthquakes or synthetic earthquakes, and the average number is about 50, which is about half of the number of wells I identified in my previous work with real data. So this clearly indicates that at least some, but not all, of the wells identified from the real data are likely coincidence between two random processes. So next I am going to just quickly show you some of the data from the injection wells, the UIC Class 2 disposal wells by region. So here, this line here, the greatest amount of disposal through time is here in this south central slice that we see. And interestingly enough, where we have the largest increase in the number of earthquakes, we do not see some change in injection properties that would match what we're seeing in the really remarkable increase in number of earthquakes. So this is a bit inconclusive. So if we look at the number of earthquakes in Oklahoma, one of the questions I always get is, how do we know this isn't an artifact of seismic stations because you had all these additional transportable array stations in the state? If we look at the number of felt earthquakes through time compared to the number of magnitude 3 earthquakes through time, and I've done different analyses that show that we're clearly complete in magnitude 3 through the time period shown on this plot. And so the number of reported felt earthquakes has roughly remained the same up until this rate change here in 2009. So that's a pretty clear indication that we're not looking at a change in instrumentation, because for felt earthquakes, those are people in Oklahoma, and our population has not increased dramatically enough to be able to explain that kind of rate increase. So one of the real advantages to having all these additional seismic stations and all these additional earthquakes is we can learn a lot more about processes that are occurring in the earth. And this is just a shot of the Prague sequence for the larger events that I was able to calculate focal mechanisms from the regional seismic stations. And here's the fault. The major portion of the map fault is right here, and this is a fault splay that comes off the major portion of the map fault. And the focal mechanisms represent the orientation of the possible faults on which the slip occurs for these aftershocks, and they all pretty much line up right on that fault plane, which is really nice to see. So one of the things I did was I looked at focal mechanisms not just for the Prague area, but for all of Oklahoma. Prior to EarthScope coming into Oklahoma, we have very few focal mechanisms, but I took and lumped all these together and calculated the likelihood of fault orientations and their activity, and so I can identify fault orientations that would be more likely to have an earthquake, shown in red, and fault orientations that are less likely to have earthquakes, shown in green. And thank you very much.
Thanks. My name is Cliff Frohlich, and I'm speaking about 3 presentations on Texas earthquakes and their relationship to natural gas development. Later today at 4 o'clock, I'm giving a presentation on a survey I did of earthquakes in the Barnett Shale in northeast Texas. The Barnett Shale is interesting because there's been development of this fracking and natural gas since about 2002, and so it's sort of ahead of other areas like the Marcellus and the Haynesville where there's development in the Eagle Ford. So it's a good place to look at how this relates to earthquakes. Friday at 3 o'clock, Wesley Brown, who's an associate professor at Stephen F. Austin University, is going to talk about an earthquake that occurred in East Texas, very close to his university. Wesley is here today. And this earthquake, there's been suggestions this earthquake might be related to fluid injection, and we'll speak about that. And finally, the third presentation in Michael Brunt, who's also here today. Michael Brunt is a teacher at Eagle Pass High School in Eagle Pass, Texas. And Michael led the effort on the earthquake in Timpson to interview people on the ground about what the shaking was so we could get a more precise location about where it occurred, as opposed to the locations that were determined from distant stations. Michael also did a similar felt report study on an earthquake southeast of San Antonio. Okay, now, so we're talking about 2 magnitude 4.8 earthquakes in eastern Texas that occurred in the last 2 years. There's the earthquake in East Texas here, magnitude 4.8. The earthquake southeast of San Antonio called the Fashing earthquake in 2011. And then I'm talking about earthquakes in the Barnett Shale. The Barnett Shale is this area here, just west of Dallas. And the question with earthquakes in these areas is, what is their relationship to natural gas development, especially the new kind of natural gas development that's raising all the ruckus? And now the unconventional gas development to develop a well, there's really 4 steps. First of all, you have to drill the well. Second of all, you pump in high pressure water to hydrofrack the well to increase the permeability so the gas will flow out. The third step is you produce the well, you let the gas flow out of the well, and when you do that, some of the hydrofracturing water that you pumped into the well comes back out, and the fourth step is you have to dispose of this frack fluid because it's dirty water and you can't just dump it in the creek. So what is the relationship of all four of these processes to earthquakes? Well, as far as I can tell, I'm unaware of any study where drilling a well has ever caused a significant earthquake anywhere. So that's not a problem. Hydrofracturing, at least in Texas, I'm unaware of any situation where the hydrofracturing in Texas caused an earthquake large enough to be felt by people at the surface. Although Austin Holland spoke of some areas, there's a handful of situations on planet Earth where hydrofracturing has caused small earthquakes. For practical purposes and in Texas, hydrofracturing is not a problem. Please get this right. And when there's headlines that say, you know, scientist says fracking causes earthquakes, this is bad. People are using fracking as a generic term for the whole process, but this drives the industries nuts, and it's not the fracking that's the problem most of the time. Well, what about producing gas and the frack fluids? Well, there's situations where producing gas and oil in fields has apparently caused earthquakes. We will say this is possible for the earthquake in Fashing, southeast of San Antonio. However, the situations are where you have huge volumes coming out of the wells, and not the situations where out of whole fields, and not the situations involved with the fracking where you have a well that's just a single well that's producing. So production has not been a problem in most areas that we're concerned about. Finally, the disposal of the frack fluids, as Art mentioned, in some cases, this is linked to earthquakes, or at least earthquakes occur near disposal wells, and we're going to show that it's possible that this is responsible for the earthquake in Timpson in East Texas. Now, from the standpoint of a seismologist, everyone you listen to here, we hear about earthquakes and we show they're near injection wells, and so you get the sense that, you know, injecting is really dangerous, but there's another view. I'm a seismologist in Texas, but most of the people in Texas who call themselves seismologists are actually oil company seismologists. And if you talk to them, they would say, hey, we're injecting all the time and we don't get earthquakes. In this map, every yellow square is an injection disposal well. There are more than 10,000 active injection disposal wells in Texas. In the Permian Basin, they've been injecting since the 20s. In the Panhandle, they've been injecting since the 20s. So if you're an oil company type, your attitude is, what's the problem? We've been injecting huge volumes for decades, and there wasn't a problem. What's the problem now? But in any case, we're going to show that the Timpson earthquake, there was a disposal well within 3 or 4 kilometers of the highest shaking area. In the Fashing case, the argument is that the closest injection wells to where the highest shaking area was, where the earthquake was about 15 kilometers away. Also, the epicenter of this highest shaking area is within a producing field where earthquakes have occurred since the 1970s. There's papers on these earthquakes showing that they didn't start until the field was developed as a producing field, an extraction field in the 1950s. And so Occam's razor says, why are we suggesting that the 2011 earthquake has any different cause than all the earthquakes that occurred since the 1970s, which are probably related to production and not to injection. Okay, now what about my survey in the Barnett Shale? Well, the motivation for this is that seismologists like ourselves, we typically study earthquakes that might be triggered by injection wells only after a quake occurs that provokes citizens in the media. I mean, that's what happened in the Timpson earthquake and the San Antonio earthquake. I go to work someday, I get calls, a dozen calls from your colleagues, and they say, earthquake occurred. And so I mobilize my colleagues and we go out and study it. And sure enough, we find that it's near an injection well. And so we just have the sense when you talk to people like us, is, boy, injection, causes earthquakes all the time. On the other hand, this is a very bad way to do a sample. I mean, suppose you lived on a desert island and you had never seen a car or used a car. The only thing you would know about cars is when you read about them that they would cause accidents. You know, there are people dying and they're running into each other. You would have the sense that cars were very, very dangerous, and your advice would be, don't go to places like San Francisco where there's lots of cars, and if you do, stay out of cars because they're dangerous, okay? And so what I wanted to do is do a study where instead of waiting until earthquakes happen and we find they're related to injection, is ask, well, how commonly are earthquakes related to injection wells in the Barnett Shale? And I think the significance of my study is that it's possibly this is the first study where people have done that. Almost all the studies you find on injection-related earthquakes occur when people notice earthquakes and then go study them rather than when people do a survey to see where the earthquakes are. So that's what's significant about my study. Well, what were the survey results? In this slide, the gray area is the Barnett Shale. The red circles are earthquakes that I located in my survey. The reason my survey was timely is that the program called EarthScope, throughout the last 20 years, most of the time, there's only been one seismic station in the Barnett Shale, and so you couldn't locate earthquakes very well. Because of this earthquake program, during my study period, there were 25 stations, and so we could locate a lot more and a lot smaller earthquakes. And so here the red circles are earthquakes in the Barnett Shale, and we found about 8 times as many earthquakes has been reported by the USGS. This is not because the USGS didn't do good work, but we had a lot more stations, and we were looking for the rotten little earthquakes, whereas they tend to locate the larger ones. The yellow squares are higher volume injection wells, wells with more than 150,000 barrels maximum rate per month, which is 24,000 cubic meters. And then the white squares and the pluses are lower rate wells. And so when we looked to see whether we would find wells, find earthquakes, indeed we found many earthquakes that weren't reported by people or by the USGS. And all the earthquakes that we found that we could locate very accurately, that is, we had good data, were near wells within 2 miles or 3.2 kilometers. And they were all near these higher volume wells, wells that had more than 150,000 barrels per month maximum rate. On the other hand, like a lot of science projects, you know, you answer some questions, but it also raises new questions. First of all, there's many wells that were higher volume wells that had no quakes. I mean, there were some of these in Johnson County here, in Parker County, and here over in Stevens County. There's higher volume wells. They've been going for a while, no earthquakes. And so why is it that we have earthquakes near some wells and not near other wells? This is actually this square here where the earthquakes occurred. This is going into the square. What we have here is, you can see that all the earthquakes, the red circles, occurred near higher volume wells and clusters. This is the Dallas-Fort Worth earthquakes. These are earthquakes near Cleburne, but there were also these other clusters in Johnson County. There's an earthquake here in Hood County, and so on. And so I think the implications of my study are, if you're trying to do policy or regulation, we need to have surveys rather than just responses to bad earthquakes. Or if you're a company who wants to manage your seismic injection, you would like data so you can manage it to minimize hazard in a responsible way. In the past, that hasn't really happened. My study is a first step in the Barnett Shale where we've done that, and I and possibly colleagues I don't know about are in the process of looking at other areas like the Eagleford Shale in Texas, like the Bakken in North Dakota, like the Haynesville in Louisiana. Over the next year, I'll be looking there to see if we get similar results. That is, in other areas, do we see earthquakes near wells or not? In other areas, do we say that they're only near wells with a certain rate of injection, a maximum rate of injection, or not? And from this, I think the ultimate thing is that if we do regulation in some areas, or if operators of injection wells want to do responsible injection practices, this is the kind of surveys that will be necessary. Thank you.
Putting the floor for questions. Do we have any questions here in the room from news reporters?
Yeah, Art, on your figure of injected volume versus maximum magnitude, volume goes out to 10 to the 7th cubic meters. How does that compare with general practice? Are there larger volumes injected in some wells, or?
There may be, Dick. I haven't done an exhaustive survey of well volumes. I think that's probably among the highest, those wells in the Raton Basin in southeastern Colorado, but I wouldn't be surprised if there are other wells that have injected higher volumes, which goes along with what Cliff was pointing out, that not all wells seem to produce earthquakes, even high-volume wells.
I have a question from the internet. This question is from Mose Bouchel from NPR's State Impact Texas, and that question is, what policies might mitigate the risk of earthquakes?
Could you repeat the question?
Sure. What policies might mitigate the risk of earthquakes?
Was that directed towards anyone?
To the panel.
To who?
The Oklahoma Geological Survey is not a regulatory body, and we've made some recommendations, but the regulations become a lot more challenging because, of course, the oil and gas industry has a significant lobby and an interest in providing domestic energy.
I might comment, none of us here on this panel are expert on regulatory issues. One thing that is important to keep in mind is that different areas are different. For example, in West Texas, you could have a large earthquake and it wouldn't affect people very seriously because population is low. A medium-sized earthquake in Dallas-Fort Worth can be serious. So I do think that any regulation needs to take account the population and infrastructure.
Rich Monastersky with Nature. This is a question for Art about that magnitude plot again. There were only a handful of quakes that you had on that. So what I'm wondering is, you know, how sensitive is your analysis to the small number of quakes you have? If you look at other magnitude relationships in seismology, if you only have 9 points or something, you know, do you really get an accurate portrayal of what the magnitude distribution is?
Yeah, that's a good question. As time goes by, we're getting more and more points on the plot, and hopefully gaining confidence, although maybe we'll start finding counterexamples. Time will tell. I haven't presented an exhaustive set of data that bear on this issue, but these are from studies that have been published and well documented. And as time goes on, we'll be getting more and more, and either getting more confident or perhaps less confident about what I was trying to show there.
I have another question from the internet. This question is from Mike Sorgan from EnergyWire, and his question is for Dr. McGarr. Why would the maximum magnitude have, excuse me, it just scrolled up. Why would the maximum magnitude have more to do with the energy stored up in the fault?
My analysis, which I didn't take time to show here, indicates is independent of the total amount of energy that is stored up on the fault. That is, the total amount of energy released by the fault might be quite a lot larger than the energy that's accounted for by the maximum magnitude earthquake. It's basically, if the earthquakes are assumed to offset the perturbation to the crust caused by the injection of whatever volume of fluid that you inject. It's not tied to the total amount of energy in that same fault zone.
I have another question from the internet. This one is from Leo Enright with Irish TV. And he says, can you explain the term completed well? And also, what is your impression of worldwide research in this area? And this is for anyone on the panel.
So when I used the term completed well, I was referring to a well that was finished and ready for production. And in that process, the majority of those are hydraulically fractured or hydraulically stimulated. And so that's the way I meant the completion of wells.
James Beal of Freelance. I have one question about the volume. If the volume of injection were in terms of a cup of coffee, we could put all the coffee in one table, or we could spread it throughout a large volume of the crust. And is there any thought or knowledge on whether you need a certain areal volume of crust to generate one of these earthquakes versus just a amount of fluid that could be in a very small volume? And the other question is, where these earthquakes are initiating, is that far below the depth of injection, and is it assumed that there's pore fluid connection between injection and the source of earthquake?
Okay, taking the first question first, liquid is injected through the injection interval, maybe at 2,000 meters depth usually into an aquifer. And from there it percolates out along the aquifer to greater and greater distances from the well with time. So near the well, the pore pressure increase will be maximum, of course, and as you get further away, it'll diminish. But as far as producing a maximum magnitude earthquake, the two effects tend to cancel each other out. If the earthquake occurs near the well and the seismic deformation is focused near the well, then it will tend to have a higher stress change corresponding to the higher pore pressure, presumably. Whereas if the earthquake occurs some distance from the well, like say 5 or 7 kilometers, the pore pressure perturbation would be smaller, but the area affected would be much greater, or the volume affected, and so they cancel each other out in terms of what produces the maximum earthquake. So the short answer to your question is it doesn't make any difference, at least as far as my analysis is concerned. And for the, let's see, the second question was involved where do the earthquakes occur relative to the injection interval. Generally, the earthquakes occur at depths that are comparable to where the water is injected or deeper. It's common to have earthquakes occurring as much as 6 kilometers deeper in some cases. The water has shown an ability to permeate along, say, fault zones quite readily, and so the hypocenter of the earthquake, where it nucleates, need not be adjacent to the well bottom.
I'm just going to bring it back to a question from Leo Enright from Irish TV, and that was about the worldwide research on this. And his question relates to the perception that many have that reports on fracking are surveys of surveys. How good is the world effort on real data like these?
Well, a brief history of this research. First of all, it was established in the 1940s that man's actions could cause earthquakes when they were filling Hoover Dam, Lake Mead behind Hoover Dam, and there were earthquakes associated with the filling of Hoover Dam. It was established in the 1960s that injection of wastes could cause earthquakes when a series of earthquakes occurred near Denver. the Army was injecting wastes in the Rocky Mountain Arsenal, and I'm not sure they ever said what they were, but they were probably related to nerve gas or something. Since that time, there has been sort of sporadic research in a number of areas when earthquakes occur. As I discussed, sometimes we go out and find that they're related to injection. There's also been a considerable effort in the last 20 years about developing of geothermal energy. So there's a number of focus studies in areas like Basel, in several areas. There's a field in California, whose name I've forgotten, and a field in Southern California, and Southern Colorado. So there's been a lot of instrumentation of fields related to geothermal energy. There hasn't been a systematic effort here or elsewhere to look at injection-induced earthquakes just at sort of single wells until in 2008 there were earthquakes near Dallas-Fort Worth that we looked at, and then subsequently some happened in Oklahoma, some happened in Arkansas. There were earthquakes in England, earthquakes in the Horn River of British Columbia. And so the recent concern, the reason you're here and we're here today, has really ramped up since 2008. So it's a sort of a renaissance of interest in this.
I have another question from the internet. This question is from Jim Fuquay at the Fort Worth Star-Telegram. And this question is for Cliff. Is there a direct relationship between an earthquake and the presence of a high volume injection well? The quakes in Denton and Northeast Tarrant and, Denton County, Texas, Northeast Tarrant County, Texas, and also the ones in South Johnson County, those seem to be clustered at the injection well site. And he adds, to clarify, isn't it fair to say that there's enough evidence to say that there's a cause effect at those sites?
Well, some of that's in the eyes of the beholder. I'll first mention the earthquakes in Dallas. In Dallas, in 2008, there were earthquakes, and colleagues of mine and I located them. We found there had been no earthquakes there in the 150 years before the earthquake started. It was 6 weeks after injection started. The earthquakes were within 1 kilometer of the injection well, and the earthquakes were at about the depth of injection. On the other hand, Leo Eisner and Jansek have published a paper in the SEG stating that they don't think that they're related. And I say this not because I disagree, but it's almost impossible to prove with certainty that any earthquake is man-made. It reminds me of the situation with smoking 50 years ago. We all know people who get lung cancer and never smoke. We know people who smoke their whole lives and don't get lung cancer. So any individual, you can't really prove that smoking causes lung cancer. The situation is true with earthquakes near injection wells. For any earthquake, you can't show that the injection well with 100% certainty caused the event. However, in the Fort Worth Basin and elsewhere, if you do statistics, you can certainly show that the injection must be causing the earthquakes just the way we can show that smoking must be causing the lung cancers.
I have yet another question from the internet. This one is from, pardon me, Mike Sorian again at Energy Wire. And this question is, could Dr. McGarr and Dr. Frohlich address the doubt that Dr. Holland raised about the lack of proof that injection has caused earthquakes?
Can you repeat the question?
Certainly. Could Drs. McGarr and Frohlich address the doubt that Dr. Holland raised about the lack of proof that injection has caused earthquakes?
Let me respond and then I'll let them. I've never doubted that injection can cause earthquakes. I feel it's important to, as accurately as possible, identify whether an earthquake is likely induced. And one of the reasons for that is because when an earthquake is identified as induced, it is no longer considered within the earthquake hazard map, the USGS seismic hazard map. The current policy is to remove those events, and we clearly know that they are releasing stress that is accrued through natural earth processes. And so I think it's important to either address the issues of how the seismic hazard maps call those out, or to be very careful when we identify an earthquake as possibly induced.
Yeah, I'll just try to follow up on what Austin just said. Part of the USGS responsibility is to assess the seismic hazard of the United States. The USGS produces maps of seismic hazard expressed in probabilistic ground motion, and these maps are updated from time to time as new information becomes available. And it's become clear recently that induced earthquakes are making a significant contribution to the hazard, particularly in the central and eastern U.S., where the natural level of seismicity is lower than in the west. Having said that, part of the uncertainty, which I think gets to your question, is whether the earthquake that we label as induced is really induced, or whether it's a natural earthquake that we mistakenly took for being induced. And I suspect that in practice, those earthquakes where there's uncertainty as to their origin will just, that uncertainty will just be lumped into the general probabilistic uncertainty concerning those earthquakes. You know, I don't know how many, or probably none of you have ever been involved in these activities where groups of experts get together and try to make decisions on how to deal with seismic hazard, but they set up logic trees, and I think induced or natural would be one logic tree branch in these deliberations in the future.
I'd also like to make a brief comment about hazard. Historically, the largest injection-related earthquakes have been about magnitude 5.5 in Denver in the 1960s, and possibly one of the Oklahoma earthquakes was 5.6. Of course, this is a significant earthquake that can cause quite a bit of damage if it's in an area like Dallas or a populated area. However, if you go to the hazard literature, almost all the concern about costs and loss of life is for earthquakes larger than 6. There is no evidence that I have seen that sort of little induced earthquakes snowball into big magnitude 6 and 7 earthquakes. So the problem with induced earthquakes at this point is that it does seem that some induced earthquakes can be magnitude 4.8, maybe even 5.5, but this is not in the range where we're talking about, you know, vast disasters.
Thank you very much. We're going to have to conclude this press conference now. We've run over a little bit, so if you could please, if you want to continue speaking with the speakers afterwards, I would appreciate it if you would take the conversations outside the room. And thank you very much, speakers, for being here and your presentations.